Hello, this time we're going to explore the question of what is a linear transformation. And well, to begin with this, let's informally make a definition. So, a linear transformation is a function that preserves vector addition and scalar multiplication. Right? So now let's define it formally so that we can actually use it and being able to distinguish which functions have this property. So formally, let U and V be real vector spaces and T a function with domain U and codomain V. Well, T is a linear transformation I'm going to underline it here from U to V, provided that the following occurs. First, well, we have to preserve vector addition, but let's put it formally. For each U1 and U2 in U, we have that T of U1 plus U2 is equal to T of U1 plus T of U2. Second, for each U in U and R real number, we have that T of R of U is equal to R of T of U. Right? In other words, the scalar product is preserved. Now let me provide an example and we'll go into the details of demonstrating that indeed it is a linear transformation. So we're going to take T going from R2 into R3, where T of the vector x, y, a vector in R2, is given by the following expression. X plus y, x minus y, 2x plus 3y. Okay. We will show that T is indeed linear. How? Well, we're going to use a template provided in the definition itself. So first, we're going to let U1 and U2 be in R2. So these are two vectors on the plane, right? Then we can describe U1 by its coordinates x1, y1, and we can describe also U2 by x2, y2. So whenever we write addition, right, of U1 and U2, so U1 plus U2 under T, this might be rewritten as T of x1, y1 plus x2, y2, which of course we may rewrite simply as follows. T of x1 plus y1, sorry, not that one, but x1 here, plus x2, and y1 plus y2 on the second. Now that we have it in this fashion, then we're ready to apply the definition of the transformation itself. And now this becomes something that resembles this. So this is t, well, no longer t. This is just by the definition given by the following vector. X1 plus x2 plus y1 plus y2, and then x1 plus y plus x2 minus y1 plus y2, and then 2 times x1 plus x2 plus 3 times y1 plus y2. But then this one, we may also rewrite it in the following way. We can decompose it as x1 plus y1, x1 minus y1, 2x1 minus 3 plus 3 y1, plus x2 plus y2, x2 minus y2, 2x2 plus 3y2. And now, well, we see that this actually corresponds to t applied on the vector x1, y1, and t applied on the vector x2, y2, which of course we can simplify it as t of u1 plus t of u2. Right, for the second part, well, we use a template provided here, and we set let u in R2 and let R in R, so a real number. Then we describe u as x1, y1. So we have that t of Ru is equal to t of R times x1, y1, right? Then we apply the definition of the scalar product, which is t of Rx1 and then Ry1. Well, now we'll go for the actual definition of t, and we expand it. So now this becomes Rx1 plus Ry1, Rx1 minus Ry1, and then 2Rx1 minus 3Ry1, which of course we now may define, right, by factoring as follows: Rx1 plus y1, R times x1 minus y1, and then R times 2x1 minus 3y1. Well, we can see that from here we may factor R by scalar multiplication, and this is just as follows: x1 plus y1, x1 minus y1, and 2x1 plus, plus 3y1, which is of course R of t of u. Okay. Hope that you like it. And well, for the upcoming video, you will see, well, how to represent matrices, how to use matrices as linear transformations.